Hi class, today we are learning something about something called the dot product. So when we look at vectors, we've already learned how to add and subtract vectors, but we haven't talked about multiplying vectors. And there's not one way to multiply vectors in a way you might think. There's kind of two different multiplication styles we do with vectors. And the first one is the dot product. So the dot product actually gets you a scalar result, which you'll see in a moment. So first, I'm just going to go ahead and define what the dot product actually is. Then I'll do a little bit of an explanation as to why the formula works. There's a separate document for that. And then we'll go forward into using it. So you don't really have to understand why the dot product is what it is. But obviously I know a lot of you will want to know that. So kind of, if you just memorize the formula, that's good enough for now, but it does help to have a bit of understanding. So if you have two vectors, I'll call them A. Is that what I do here? Sorry, I'll call this one. These were U and V. I know you guys don't like U and V, but oh well. So I'll call this U, and I'll call this V. And then when placed tail to tail, they have the angle theta between them. So the definition of the dot product of these two vectors is you do U and then you put a dot V. And in this case, it's the magnitude of U times the magnitude of V times cos theta. Okay, so, and theta has to be between 0 and 180 degrees for this to work. Okay, so you might be wondering, where does this cos theta come from? What on earth is going on? Well, if you go to the other document I gave you, really it talks about why is this cos theta. So really, to multiply two vectors, it only makes sense to multiply their lengths together if they're pointing in the same direction. So cos theta actually comes from, if you want to take this, in this case, this vector A, and put it alongside B, then you can do that. It's like taking a flashlight and saying, what kind of shadow does this make on the other vector? So if you actually use SOHCAHTOA, this can make a bit more sense to you. So if you're wondering where this comes from, it's because this is the right triangle that they're showing here, where this is it. Okay, so if this is your A and this is your theta, then to come up with this, you could say, let's call this X. So cos theta is X over A. So X is just this is vector A. So this is just the magnitude of A cos theta. So that's what this means here, that this length here in the right triangle is just A cos theta. It's like taking a light and shining down. How long is this on B? Okay, and then you multiply the magnitude of that times the magnitude of B, and that's what the dot product is. So look that it actually doesn't matter if you project or kind of take how long B is onto A, then this would just be the magnitude of A, and then this length would be B cos theta. So you can do it in either way. So again, this document that I'm talking about right now, it's not going to be testable. It just gives you a sense of where this formula comes from. So really we're saying we're taking how long V is, if we put it along U, and then we're multiplying the length of the V in this direction times the length of the U in that direction. And that's a way that we can multiply two vectors together. And it does get us, you might be like, well, how is this useful? Well, it's going to be useful later when we calculate work, something called work. And it's going to be useful when we do way later determining the equation of a line in R3. So it does have applications, they just won't quite come yet. But trust me, we do use it. So the result is a scalar. So when you multiply the magnitudes together times cos theta, you get a number. So that it's not a vector, it's actually a scalar, the result, and it can be negative, positive, or 0. And the result of that will depend on theta, because the magnitude of both of the vectors will always be positive. So therefore, it's the cos theta that will give you whether it's positive, negative, or 0. So if it is an acute angle, then cos theta is positive. And so then the dot product will be positive. However, if theta is 90 degrees, then think about that. Cos of theta is 0. So therefore, the whole dot product will be 0. This is very important. We use that in problem solving later with perpendicular lines. We use the fact that their dot product is 0. Okay, and then if our angle is obtuse, then cos theta will be negative. So then our dot product will be negative. Okay, so example 1, two vectors have magnitudes of 3 and 5 respectively. There's an angle of 120 degrees between them. Note that we know that it will be a negative dot product because this is an obtuse angle. So we can just say A dot B is equal to 3 times 5 times cos 120 degrees. Okay, so this gives us negative 7.5 as the dot product. Okay, some properties of the dot product. So I'm just going to show these ones, and then number 4, I'm actually going to do a little visual proof. So the commutative property says that P dot Q is equal to Q dot P. So this is because P dot Q is just equal to the magnitude of P times the magnitude of Q cos theta. And so because these are just numbers, we know that this is commutative, so we can write it in this direction. And this angle between them stays the same, and so that is just Q dot P. So a simple little explanation of this. Okay, the magnitudes property is that if you have a vector dotted with itself, then you get just the magnitude of that vector squared. Why is this true? Well, because P dot P is equal to the magnitude of P times the magnitude of P times cos 0 degrees, because there's no angle between them. And so that is just equal to 1. So that's why you get that squared. Okay, the associative property is that if you have some k that's a scalar times a vector P times vector Q, that can be rewritten as P and then the scalar moved to Q like that, or it can be written as Q times the dot product of P and Q like that. Sorry, K times that. Okay, so note that, though, something that is not true, I'll change this to red. If you have A dot B dot C like that, this does not equal A dotted with B and C like that. And that's because this result is a scalar. So you get whatever scalar out of here, multiplying dotting with C, and this is also, but this would be a different scalar. So it doesn't work. You also can't dot a scalar with a vector. It doesn't make sense. Okay, so this next one is the distributive property, and I'm going to actually do a little visual explanation of this guy. So first of all, draw this diagram. So you have vector P, which we've labeled AF, and then Q and R, and then I've labeled the coordinates there. So that means that this vector here is just Q plus R using the triangle law. Actually, I don't like it there. I just know where I'm going to have to write other stuff, so I'm trying to. So we go right along there. Q plus R. Okay, so I'm also going to draw some other features. Okay, I'm going to drop down a perpendicular. Okay, hopefully yours looks more perpendicular than mine from there, and a perpendicular from here as well. So I'm going to say that this is D, where it hits here, and this is, what did I label that as? E, where it hits here. Okay, and so we're going to prove that P dotted with Q plus R is equal to P dot Q plus P dot R. So that's what we're setting out to prove, this guy. Okay, so let's start with defining Q dotted with P. Well, that would be equal to the magnitude of Q times the magnitude of P, and then Q and P, so this would be the cos of angle BAF. Okay, but notice, different color here, notice that AD, from the right triangle AD, can be rewritten as Q, magnitude of Q, cos BAF. Okay, so that's in this right triangle here. We can just use SOHCAHTOA to rewrite AD in that way. Okay, so that means I'm going to go back to this and rewrite it as P times AD. Okay, because what you have left then is Q cos BAF, and that can be rewritten as AD. Okay, so that is one thing. Okay, now we're going to do something similar with R dotted with P. So R dotted with P. So now I've created this new diagram. So I've just taken R and just moved it down so it's dotted with P. So this coordinate here could be seen as B or D. I'm just putting it down. This is C. And then here is E. And this is F. Okay, so I've kept my P. I've just taken R and moved it down to D. Okay, so R dot P is equal to the magnitude of R times the magnitude of P times cos CDE. But similarly as above, we can rewrite DE as the magnitude of R and cos CDE. Okay, so that's just using primary trig. So our R dot P can be rewritten as the magnitude of P times DE. Okay, so notice I've represented Q dot P and R dot P. So now I'm going to do Q plus R, which is this vector here, dotted with vector P. Okay, so that's this. Now I'm looking at this CAF, like here AC, that's the vector Q plus R, and then AF, that's the vector P, and I'm dotting them together. So this is the magnitude of Q plus R times the magnitude of P times cos CAE. Now, using similar logic up there, I'm just going to replace Q plus R and cos CAE with AE. So I can rewrite this as the magnitude of P times AE. Okay, that's using the same logic as up there. So, as a result of all of this, we get that Q dot P plus R dotted with P is equal to AD magnitude of P plus DE magnitude of P, which is equal to AD plus DE magnitude of P. So AD plus DE can be written as AE times the magnitude of P which is equal to Q plus R dot P, as shown up here. So this shows through the series of equal signs that those two equalities hold true. Okay, so now let's work into some examples. So our first example is uses the dot product to find the angle between 2 points, or sorry, between 2 vectors. Okay, now this is really important. Again, it comes up in problem solving later on. So recall that this is the dot product formula. So if we know the magnitude of both vectors, which we do, and their dot product, which we do, then we can rearrange this formula for cos theta and just sub in what we know. Sorry, over. Get rid of that equal sign. Okay, so this is just equal to 12 root 3 times 8 times 3. So this is 24, so 12 over 24 is 1 over 2, so you get root 3 over 2. So from our special triangles, we know that theta is equal to 30 degrees, because it says to the nearest degree. Okay, so that's example 2. Example 1. Example 2, if a plus 3b and 4a minus b are perpendicular, a equals 2b, magnitude of A is 2 times magnitude of B, determine the angle between A and B. Okay, so if they're perpendicular, this means that their dot product is 0. So that is the first thing we got to understand. So a lot of the questions are going to revolve around the fact that the dot product is 0 if they're perpendicular. Okay, so that means A plus 3B dotted with 4a minus b is equal to 0. So this means 4a dot a plus a dot b plus 12a dot b minus 3b dot b is equal to 0. So remember that when 2 vectors are dotted together, the same vector by itself, that this is just the magnitude of that vector squared. Okay, and we can collect this to be, sorry, this should have been minus a dot b here. So this is plus 11 a dot b. And this is minus 3, and then the magnitude of b, all squared, equals 0. But remember that the magnitude of A is equal to the magnitude of 2 times B. So the magnitude of A all squared is equal to 4, sorry, there shouldn't be a square there, 4 times the magnitude of B squared, if you square this whole thing. So instead of an A squared there, I can put in a 4 magnitude of B squared instead. So you get 4 times 4 magnitude of B squared plus 11. And then instead of A, we can put 2B times the magnitude of B. Okay, cos theta. That's the dot product there. Okay, minus 3 magnitude of B squared equals 0. Okay, put this to the side. Okay, so this gives us 16 magnitude of B minus 3. So you get 13 magnitude of B squared plus, and then 11 times 2 is 22 magnitude of B squared cos theta equals 0. Okay, so then you can rearrange and isolate for cos theta. Sorry, I'm running out of room. You get cos theta equals, so I move the minus 13. Oh, shoot. Sorry, guys. Minus 13 magnitude of B squared over, and then you divide it by 22 magnitude of B squared. So these cross off. So you're left with just negative 13 over 22 as your cos theta. And so you put that into your calculator and you get 126.2 degrees. So we're using a lot of new learning in here, okay? So we're using the fact that the dot product of two vectors just is the magnitude squared of that vector. We're also using the dot product definition here, and we're using a fact that it gave us in here about these two being equal to rearrange, okay? So there are similar questions like this in the homework, so take some time to maybe pause the video and re-look at this problem, highlight anywhere you might not understand, and make sure you do go through the effort of understanding that example. Okay, the last example involves, we're gonna make a diagram to help us understand that. So prove that if the magnitude of x plus y equals the magnitude of x minus y, prove the non-zero vectors x, y are perpendicular. Okay, so if we can imagine this, they're saying if we have an x plus y, so they're saying if the magnitude of x plus y, which would be this resultant here, right? So they're saying if that magnitude is equal to the magnitude of x, and then, sorry, these should have arrows on them. They're saying if that magnitude is equal to x minus y, which would be this vector here, then this has to be a 90-degree angle. If it wasn't, then this wouldn't be true. So visually that makes sense because it has to make a rectangle instead of just a mere parallelogram for these diagonals to be the same. So I'm going to set up an equality assuming this is true, and then you'll see what happens. Okay, so just sit back, relax. Don't freak out that you should have known this, but this is a good exercise in what can be done mathematically. So what I'm going to do first is I'm going to square both sides. Okay, so this is then the dot product of x plus y dotted with x plus y, okay, moving backwards with that definition. And so this is equal to the dot product of x minus y with itself. Okay, so then this can be rewritten as x dot x plus 2x dot y plus y dot y. And this can be written as x dot x minus 2x dot y plus y dot y. Okay, now this can be written as the magnitude of x squared, and then plus 2x dot y. And this can be rewritten as the magnitude of y squared equals, again, the magnitude of x all squared minus 2x dot y plus the magnitude of y all squared. So now these here are all scalars. This result, all scalars. So, and they're the same on either side, so they can be taken away. We move this to the other side and we get 4x dot y has to be equal to 0. So x dot y has to be equal 0. And therefore, since that's true, the x must be perpendicular to y since their dot product is 0. Okay, so there's some techniques for you of how to do a little proof using the dot product. So thanks for watching, guys. Hope you learned lots.